Hello and welcome again to my Physics Online video lecture series. Today's video is about forces between charges. So this is going to be focused on Coulomb's law with point sources. So if you're making it to this video, you should be sort of reading the relevant chapter on charge and force between charges in whatever physics book um, of your choice. Obviously, if you're taking a class from me, that should be the actual book associated with the class, but you should be reading that section. So you should know that there are different charges. So in some sense, we could call this the recall part of this video, or the review part. Recall that there are two types of charge in nature. These are positive charges and negative charges. Also worth noting is that in more modern physics, meaning like late 19th, early 20th century discoveries of the structure of atoms and whatnot, that negative charges are associated mostly with, though not exclusively to, electrons, and positive charges are associated with though not exclusively found in atomic nuclei, specifically the protons. So the charge of an electron is the elementary charge negative value. The charge of a nucleus is the number of protons, basically the atomic number Z, times the elementary charge. This is a E for elementary charge. And that elementary charge E is a fundamental constant of a universe, and it has a value of about 1.602177733 times 10 to the minus 19 coulombs. Now, I think our entire unit system has actually been sort of redefined so that that's kind of an exact number, and that kind of defines actually a coulomb more so than the elementary charge. But last but not least, the coulomb is the fundamental unit of charge. This is in fact a base unit in the modern SI system of units. So this is basically the main stuff to recall. It might be worth going and looking up values of other kinds of point charges and so on. Like you could look up muons, you could look up alpha particles, which are basically helium nuclei. You can look up protons and neutrons and antiprotons and positrons and so on. All of these things have associated with them some rest mass and some amount of charge. And so those are kind of like the commonly used particles that may or may not have a specified charge value. The main one to know is this elementary charge, and that for any kind of atomic nucleus, you need to know how many, what the atomic number is, and you can multiply by that elementary charge to get the total charge. So for example, if you have helium, Z is equal to 2 for helium, and so the charge of a helium nucleus, which is also an alpha particle, is 2 times this number. We often, by the way, approximate this number as just 1.60 times 10 to the minus 19 coulomb. We don't usually carry all these digits because we don't usually need this much precision in physics 2. Second thing to address in this video is the forces between charges. For that, I'm actually going to kind of turn to the PhET simulation. We actually do have a setup of an apparatus where you can just measure the actual force between some charges. We don't really care if we're using atomic scale or macroscopic, but I'm going to use atomic scale simply so that I have two very obvious point objects. And down here I have the charge values in terms of the elementary charge. The distances here are actually given in picometers. A picometer, 1 times 10 to the minus 12 meters. And then this is the sort of like location of each of these charges. So these two are 40 picometers apart. 30 to 70 is 40. And what you can see here is how much force in newtons is exerted on each charge, and then the arrow actually gives the direction of that force. And you'll notice these two charges are different, but we actually have the same amount of force. They're in opposite directions, but we have the same amount of force. Now, before going further, reflect on this point and see if that makes sense with what you know from Physics 1. You might actually want to pause this video and try to think of, is there any principle from Physics 1 that you might have used to predict that result? That even though I have different amounts of charge, these two have the same magnitude of force on each other and actually opposite directions. So pause the video, think about it, and then play. Okay, so if you paused it and thought about it or went back and reviewed your Physics 1 notes, you should have encountered Newton's force laws, and specifically Newton's third law, which says that for each force there's an opposite direction equal magnitude reaction force. And so that means that we would predict that these two should be equal magnitude no matter how large or small I make one or the other charge. So they still have the same magnitude as each other. The magnitude may be changing, and so you can see that force depends somehow on how much charge I have here. It also actually depends somehow on how much charge I have here. And then these arrows right now are always pointing kind of towards each other, meaning this is an attractive force. If I sort of flip the sign of this charge and make it a +2 and a +4, I have the same magnitude of charge, but both arrows just flip directions and are now pointing away from each other. So it's sort of a repulsive. If I make this one negative instead, okay, it's attractive again. And if this one goes negative again, now it's repulsive. So just from doing that, we can write a couple observations. The first is that the force between charges is attractive for opposite sign charges and repulsive for same. The second general observation is that this force between the charges depends on the amount of charge present for each of the charges, meaning if I change charge 1, force changes. If I change charge 2 instead, force changes. So that may beg the question, what if I change both of them? That may be a little of an odd thing, but there's actually kind of two other things that we could create to be our independent variable, right? So we could say like charge 1 is an independent variable and charge 2 is an independent variable, and to some extent that's fundamentally correct. But we could also say the total charge in the system, Q1 plus Q2, is an independent variable. And we can also say that the product of the two charges, Q1 times Q2, is an independent variable. So if I go back to the sort of original settings here, I end up with -2 plus 4. That is a total charge of the system of +2. So if I reduce this by 1, I also need to reduce this by 1 to make it +2. And I see that when I've done that, this seems to have changed. And so if I go back here, yeah, it's changed. But if I'm treating these things as independent variables, then in order to change the sum of charges, I still need to make the product the same value. So -2 and 4, the product is -8. So if I'm going to change this one to -1, I actually need to change this guy to +8. And what do you know? We actually have the same amount of force here. Okay, so I have changed here the amount of total amount in the system while holding the product constant, and I get a no change. And before, I changed the product of the two from -8 to -3, as it turns out, but I kept the total in the system constant. So when that happened, the force changed. Here, it did not change. All right, so this means that it depends on the sort of total charge present, not on the total charge present, but on the product of charges. All right, one more thing that we might change, which is distance. To change the distance, I just have to move one of these two charges. So if I move this charge closer, like maybe at 60 to 30, so 30, I notice that this got to be bigger. If I move it closer still, this thing is bigger still. In fact, when I move from 70 to 50, the distance has decreased from 40 to 20. So I've halved my distance. And looking at these numbers, 4.61 is pretty close to 4 times 1.15. In fact, if there's another digit after this 5, I could see that being round off error. So having the distance means quadrupling the force. And if I double the distance, so right now we're at 40, so to double the distance, I need to get to 80 apart. So let's move this guy over to the 90 mark and this guy to the 10 mark. This is 2.88. 4 times that is very nearly that 1.15 times 10 to the negative 6 rather than 2.88 times 10 to the negative 7. So this basically means that it's inversely proportional to distance between charges squared. Put differently, doubling the distance means that the force will be a fourth as much as it was before, and halving the distance means that the force will be 4 times as much as before. Now, if we put all of these observations together into a single equation, that equation basically looks like this. I can't say equals, I can say is proportional to, and I have Q1, Q2 divided by distance squared. I'm actually going to use an R for distance because a lot of these forces end up being, let's say, the force between an electron in a semi-classical orbit and the nucleus. And that is effectively the orbital radius of that electron. So we'll use an R, but R means distance between the two charges. So if I have Q1 here and I have Q2 here, then this distance represents R. Now I said proportional to. To make it equal to, I have to add in a proportionality constant. And that proportionality constant is what's called the Coulomb's constant. So I'm going to use a C, a subscript of a C, so it'll be K Q1 Q2 over R squared, and that is the magnitude of the force between them. If I want to get the direction of the force, well, that is maybe best calculated on a charge by charge basis using the attraction and repulsion rules. This K sub C is what's called Coulomb's constant. It has a value of approximately 8.988 times 10 to the positive 9 newtons times meters squared divided by the charge the charge units, coulombs squared. So this right here is what's known as Coulomb's law. We'll later introduce another constant called permittivity of free space, such that K sub C is 1 divided by 4 pi times the permittivity of free space. But that's really for another video lecture. A lot of textbooks will introduce this constant sort of right away. I will be introducing it in a future lecture. So that is Coulomb's law for a pair of point charges. Now we could do other stuff with this, like work an example, and we could consider what happens if you have multiple point charges and so on. But I actually kind of want to make that a separate video, maybe a short example for this video. As our example, let's just consider 2 point charges plus 5e and minus 4e that are 40 picometers apart and figure out what the electrostatic force between these 2 point charges is. So to basically solve this question, what you have to do is just apply Coulomb's law. This right here would represent your Q1. This would represent your Q2. This would represent your distance R. So basically we expect FC equals K sub C, Q1, Q2 over R squared. Now we need to sort of convert units. So R is 40 picometers, but that's the same as 4.0 times 10 to the minus 11 meters. Q1 is plus 5e. That's the same as 5 times 1.6 times 10 to the minus 19. So 1.6 times 5 is 8. So this would be like 8.00 times 10 to the minus 19 coulombs. This one is 4, or is negative 4 times 1.6 times 10 to the minus 19. So maybe this one right here ends up being about 6.4 times 10 to the minus 19 coulombs, or negative 6.4 times 10 to the minus 19 coulombs. So we can now plug those into this equation. K sub C, again, 8.988. By the way, I usually, when I'm using two significant digits, it's kind of easier to remember 8.99 times 10 to the 9. So very often in my examples, I'll take it to 3 digits and just round this to another 9. So that's Newton meters squared per Coulomb squared. We multiply that by 8.00 times 10 to the minus 19 coulombs. And then we multiply that by negative 6.40 times another 10 to the minus 19 coulombs. And then the whole thing is going to be divided by 4.0 times 10 to the minus 11 meters squared. So that all goes into your calculator. 2.87616 times 10 to the negative 6 newtons. If we round that off to 3 significant figures, this would give us about negative 2.88 times 10 to the minus 6 newtons as our answer here. Now, the minus sign is important if you're trying to figure out direction, but again, it really makes sense only to kind of go figure out what direction is this going to be acting on each charge individually. And I will make another video that will kind of discuss that in a little more depth. It becomes kind of important when you're dealing with more than just two charges interacting. But for today's video, that's probably sufficient. Let's go back to the PhET simulation though, because I can actually set up this exact configuration. So here's the two charges that were just mentioned. Let's put this guy back at its position of 30, which I guess is about here. I said it was 40 picometers apart, so I think that means this guy's got to be at 70, which is right here. And sure enough, 2.88 times 10 to the negative 6 newtons is what the simulation is also showing. So you can see how that matches with the number that we calculated down here. So that's all I'm going to do in today's video. Like I said, I do plan on making another one, and so look for that in the future. In the meantime, thanks for watching. Hope